Hello friends, welcome to Ace Engineering Academy online platform where we are discussing GATE 2022 questions from algorithm. This is a question for 1 mark and its category is MCQ, that is multiple choice question, and this question belongs to asymptotic analysis. The question says that which one of the following statement is true for all positive function f of n. All positive function f of n, which of the following is true? Okay. Now here we have f of n square is equal to theta of f of n whole square. F of n square is equal to O of f of n whole square. F of n square is O of f of n whole square, where fn is an exponential function and f of n square is greater function, in this case is f of n whole square. Now here let's concentrate on the option B, and here it is saying f of n square is equal to, is a lesser function order of than f of n whole square. And here f of n can be taken any function. It is not restricted to some polynomial or exponential function. Now suppose if I take f of n as a logarithmic function, log of base 2n. Suppose this is my function f of n. Now if it is the function f of n, then what will be f of n square, and f of n square will become log of base 2, and this will become n square, right? N instead of n, I'll put the value n square, and that is equal to, in this case, is 2 times log of base 2n, right? F of n square will become, in this case, is 2 times log n. Then we will take f of n whole square, in this case is f of n whole square, and here in this we have f of n whole square, and in this we will have f of n whole square, and in this f of n is log of base 2n, okay, log of base 2n and multiplied by log of base 2n. Okay, so I like here omega and O, and here f of n is this particular part here, in this case is f of n square is always a lesser function than this log of base 2n, and we need to comment about true function in this particular case. Okay, so here I can say with that I can discard here option D. Okay, discard here in this case is option D, that f of n square is omega of n square, though I was discussing B here in this cases, but I can go ahead and discard option D, that f of n is a greater function. Now here it is saying that 2 log of base 2n is greater function, greater or equal function than some c times log of log n into log n. So now this is not possible, that log of base 2n is a greater function than log n, and we can discard here with this option D. For a polynomial function, if I say like polynomial function, now if I take f of n is equal to 2 to the power of n, okay, and then in that case f of n square will become, in this case, what it will become here in this case is, f of n square will become 2 to the power n, and that will become 2 to the power n square, and f of n whole square will become what? F of n whole square will become, in this case is 2 to the power n and to the power of 2. Now here one function in this case is exponential function, and f of n square is a lesser function than, is equal to 2 to the power 2n. Okay, a small slight here updation. In this case, this is a small o, okay, this is not a big O, this is small o, f of n and whole square of it. Okay, now so here in this case f of n is 2 to the power of n, f of n square is 2 to the power n square, instead of n I'll put the value n square, and this is 2n. Now see here that for exponential function, that f of n square is a bigger function, 2 to the power n square is a bigger function than 2 to the power 2 to the power 2n, and hence I can say that f of n is not a lesser function. This is not correct, and C is also false statement in this. When I come to the option D, and it is saying strictly greater, and here for any polynomial function, this won't be this won't satisfy for any polynomial function. Suppose I take f of n is equal to n square. Okay, suppose I'll take n square here, n square plus 1, suppose if I take. Now f of n square, f of n is n square, f of n square will be what? F of n will be n square will be n square is square n to the power 4 plus 1, and f of n whole square will be what? F of n whole square will be equal to, in this case, will be n square plus 1 to the power 2, which will be in this case will be written as order of n square, n to the power 4. This is n to the power 4, this is n to the power 4, equal function, it should be strictly lesser, and hence option B is also not correct. For any polynomial function, f of n square is theta of f of n whole square, where fn is polynomial. Answer for this question is A. Quite lot of work for single mark. Okay, now this question is requires lot of understanding and thinking in the examination itself, so that you can discard other option. Few are really can be discarded, like here in this case theta small o is a simple case, though I just not written correctly, there is small error. So this is small o notation actually, and we have f of n square is order of f of n square, where f of exponential clearly guiding you here in this cases, we can easily verify, and f of n square is omega of n square. That is we have to think and come up with this f of n as a log n function, logarithmic function, and we can discard option D. Answer for this one is A. Another quite interesting function in this is consider the following recurrence, and this question category is MSQ, where f of 1 is 1, f of 2n is 2 times f of n minus 1, and f of 2n plus 1 is 2 times f of n plus 1 for n greater than equal to 0. Which of the following is true? Okay, now I really find this question like comparatively all other recursion questions a bit difficult in this case, because you need to validate the options here, and that options are not straightforward the values, but is written in some form of function actually, and that is for MSQ, that there can be multiple choice correct. So multiple times you have to know check the option in this case, right? So now let's have this value f of 1 is 1, fine, f of 1 is equal to 1, great, f of 2, so f of 2 I can write, I can use this function, f of 2 is equal to f of 2 times 1, okay, 2n, 2 times n, 2 times 1, and in this case f of 2n I can say 2 times f of n, so 2 times f of 1 minus 1, and that is equal to 1 I am getting. F of 3, which condition satisfy? Let's see, f of 3. Now f of 3 can be written in this way, 2n plus 1, 2 into 1 plus 1, and f of 3 can be written f of 2 into 1 plus 1, 2n plus 1, and that is 2 times f of n, 2 times f of 1 plus 1, and here we have plus 1. So now in this case is f of 1 is 1, and this case answer is 3. So f of 3 I am getting here in this case is 3. F of 4, what I will get here? F of 4 I will get here in this case is f of 2 times 2, okay, and here in this case is I'll get 2 times f of 2 minus 1, but f of 2 is again 1, and in this case again I'll get answer in this case is 1. So I'll just see that f of 2 to the power n is coming here in this case is 1, so that I can validate. So I'll just say f of 4, then I'll say f of 8 is f of 2 times 2 to the power 3, or like here in this case is what I'll say 2 times 4, okay, 2 times 4 I can write 2 times 4, and it will become 2 times f of 4 minus 1. F of 4 is coming as 1 and this is still 1. I have validated the first option. B is correct in this cases. Now I'll go for f of 5. Let's see f of 5. F of 5 can be written in which form? 2 into 2 plus 1. I think that is the correct one. 2 into 2 plus 1. So in this case I'll write here f of 2 into 2 and then plus 1. Okay, 2 into 2 plus 1. 2 times f of 2 plus 1. 2 times f of 2 plus 1. What is f of 2 is 1? That is still 3. So I'm getting a constant value in this case is 3. F of 3 also I got here in this case is 2 times f of 1, and here 2 times f of 2, because f of 2 is 1, that is also coming here in this case is 3 as well. Right. So f of 5 here in this case is I am getting here in this case is 3, and which can be represented as 2 to the power 2 to the power n plus 1, 2 to the power 2 plus 1, and 2 to the power n plus 1 in this cases. Okay, so here we have some issue with 5. 5 can be represented as 2 into 2 plus 1, that is 2, 2, 4, 4 plus 1, 2 times f of 2, which is 1, and that is equal to 3. Fine. F of 6 can be written here in this cases 3, f of 2 into 3, and that is equal to in this particular case is 2 times f of 3, 2 times f of 3 minus 1, and that is equal to f of 3 in this case is 3. 3 into 2 6, and that is minus 1, that is equal to 5. So f of 3 6 is coming here in this case is 5. Right. So f of 5, can I say f of 5 is f of 5 into 2 to the power 0, okay, is equal to 2 to the power 0 plus 1, 1 plus 1, 2 to the power 0 plus 1 and plus 1, and that is equal to 2, 3 I am getting. F of 5 is getting 3, and with that I need one more validation, but it seems C is also correct here in this cases. But 2 to the power 2 plus 1, D is not getting, seems to be correct here in this case, because here if I take 2 to the power 2 plus 1, forget about this 0, that is equal to 2 to the power 2 plus 1, and that is not getting correct here in this case. So now I validated this, 2 more validation is required. Like here f of 3, f of 3, so 2 to the power 3 is coming here in this case is 3. So 3 is validating A actually. 3 is somehow validating in this case is A. Let's validate with f of 7. What is f of 7? So 7 I will write 2n plus 1 form. So f of 2 into 3 plus 1 form I will write 2n plus 1, and that is 2 times f of n, 2 times f of n plus 1, 2 times f of 3 plus 1. What is 2 times f of 3? The 2 times f of 3 in this case will be f of 3 is 3. So 3 into 2 6, 6 plus 1, that is 7, and that validate f of 7, 2 to the power 3, 2 to the power 8 minus 1 7, and that is also 8 minus 1 7. This also validate option A as well, seems to be true in this case. So 5 it is not working, even 3 it is working. 2 to the power n plus 1, for 3 it was working. That 2 to the power here in this case 1 plus 1, so 2 to the power 1 plus 1, 3 it is working, but 5 it is not working. So I can say option D is not correct. F of 8 we have done. F of 9, can I check one more time for validating more? So 9 can be written 2 into 4, f of 2 into 4 plus 1. Okay, and in this case f of 2 into 4 is 2 times f of 2. Okay, 2 times f of 4 plus 1, and that is equal to also 9. 9 is coming in this case is also equal to 3. F of 9 is 3. 9 I can construct here in this case is 2 to the power n. 9, we don't have a 9 pattern in this cases, but that is not 3 actually, that is D is not there. F of 9 I'll not get from any way. Okay, 9 I will not get from any, but f of 10 definitely I will get here in this cases. F of 9 not getting it, but answer in this case is 3. 5 was 3, 3 was 3. So 2 to the power 4 plus 1, but that is not 9 here. 2 to the power 8 minus 1, no, that is not coming. So 3 is coming, 3, 5 is coming in this case is 3, and 9 is also coming in this case is 3. F of 10. that I can write here 2 times 5 f of 2 times 5, and this can be 2 times f of n, 2 times f of 5, that is 3 minus 1, and that f5 is 3, 3 into 2 6, 6 minus 1, this case is 5. You can validate this one more time, that 5 into 2 to the power 1, 2 to the power n plus 1, okay, 2 to the power n here in this case is 5 into 2 to the power 1, so 2 to the power 2, 4, 4 plus 1, 5, and that is getting here in this case is 5, that validate option C. Written too many values here in this cases, and here to solve these too many values I have also finalize the pattern. One way of doing is manually, and second way of breaking down this formula in this particular case. One another way of getting this in this case is breaking down into a formula. Okay, so that is another method, that is a lengthy method. Here we need to validate, so I find this one a little bit quicker, right? I find little bit quicker in this case, and I go with A, B and C is the answer for this question. Okay, the next question is from this MSQ category, and these are 2-mark questions. So you can see that there are 2-mark questions, plenty of 2-mark questions, and that is here. This is also MSQ, which is one of the, I'll say, not very straightforward question, MSQ, and here also we have this MSQ, which is a lengthy category. Consider a simple undirected weighted graph G, all of whose edge weights are distinct. Which of the following statement about the minimum spanning tree are true? So distinct edge weight. Now option A, the edge with the second smallest weight will be always part of the minimum spanning tree. Distinct edge weights are there, and if I just follow the Kruskal algorithm, then I'm going to add the vertex. In the I'll sort them in the non-decreasing order or increasing order and pick up the safe edge and include it. And when I'll pick up the second edge, it will always be safe. Reason is it will never form a cycle. So here A is the correct one. A option is the correct. The second smallest edge will be always part of any spanning tree of G. That is always true. If the distinct edge weight are there, always be there. Option B, one or both the edges with the third smallest and the fourth smallest edge weight part of any minimum spanning tree. One or both of the edges, which is third smallest and fourth smallest, are part of minimum spanning tree of the G in this case. One or both, either one will be or both will be the part of the third smallest edge of minimum spanning tree. Simple undirected weighted graph in this case. Now here both can be possible, that third smallest and fourth smallest is a part of a spanning tree. Yes, it is possible in this cases. Now here suppose this is 1 and this is 2. Now one or both, one of them or both of them. Okay, now here in this case is, suppose I have the third smallest edge here in this case is this. Distinct, third smallest weight. Now here, will this third smallest edge will be part of spanning tree? Will it be part of it? Will it be part of MST? Answer is no. It won't be part of it. Why? Because it is creating the cycle. And if it is not part of it, so let's have another vertex which is, let's say here in this case is 4. Will it be part of it? Yes, it will be part of it. So either I'll include, because the cycle formation may happen because of the third vertex and may happen because of the fourth vertex. But because it's a simple, both vertex will not be part of the cycle. Okay, both vertex will not be part of the cycle. Right? So either third or either fourth will be part of the cycle. Okay, so either one or both. Both can be, yes, possible, both can be, but if it is not forming a cycle here in this cases, then both can be part of the cycle. So this statement is also a true statement here in this case. The first one is true, smallest always second smallest, and third and fourth, one of them will be definitely part of it. Another will be not part of, in which case if it is forming a cycle. Now, see, suppose S is element of V and suppose that S is not phi and S is not all. not phi, not empty, not all. Consider the edge with minimum weight such that one of its vertex in S is not phi and S is not V, and another is V divided by S. Such edge will be always part of minimum spanning tree. So now here in this case is that is the minimum weight, and whose one edge is in one set of vertex and another is another set of vertex, and that is the minimum weight. So if you want to make the connectivity something like some vertex are here and some vertex are here, and there may be different ways of connecting it to this vertex, and this is 4, 10, and suppose this is 2. So definitely that if you have one edge over here, one edge over here, definitely you are going to connect with these two rather than 4 and 10. So if it is the minimum weight, it will be always part of the spanning tree. This is also true statement. Now G can have multiple spanning tree. G can have multiple spanning tree, and that statement here in this case is false because the edge weight given in this case is distinct. We'll go here in this case with A, B and C. That is the answer, A, B and C. I'll go back here. Answer for this question is A, B and C. A, B, C is the answer for this. The next question is a 2-mark question, and this category is a numeric answer type question. So we have this category as numeric answer type question, NAT, where it says that let GV be a directed graph where V is equal to 1, 2, 3, 4, 5 set of vertices, and E is the set of directed edges as defined by the following adjacency matrix. So Aij is equal to 1 if I and J I and J is greater than equal to 1 and less than equal to 5, 1, otherwise 0. Aij indicate a directed edge from the node I to J. A directed spanning tree, okay, just understand the word, the sentence. A directed spanning tree of G rooted at V is defined as a subgraph T of G such that the undirected version of T is a tree, okay, of a tree is a tree, and T contains a directed path R from every other vertex in V, okay. So its undirected version is a tree, but it contains a directed path, from R to every other vertex in V. So there is a directed path, but its undirected version is a tree. The number of directed spanning tree rooted at vertex 5 is. Now here I will come to this statement, and here first thing that we want to do here in this case is the visualization of this graph. Now here it says that there is a matrix, and here I'll just draw that matrix 1, 2, 3, 4 and 5. Now here we have the entries here in this case is that if I is less than equal to 1, so now here I is less than equal to 1, but here I is not less than equal to 1. So on all the cases there are I is less than or equal to 1, and 1, 1, 2, 2, 3, 3, 4, 4, 5, 5 satisfy this thing. But yes, I is not less than here J is less than equal to I, J is less than equal to I. So this is I part, this is J. This is not J less than equal to I. This is J, here J is greater than I, J greater than I. So now here the entries that will come here in this case is your directed entries will look like this, this, this and this, okay. So this is how this tree is, this adjacency matrix is going to look like. And what about the tree here, how the tree is going to look like? So tree will look like this. There is a vertex number 1, it will have an self loop, then there is a 2, then there is a 3, then there is a 4, and then there is a 5. Okay, now here in this case, so now there will be a loop of 2, and in this case is this is like this. There is a loop of 1, and then there is a directed edge to 2 and then 1. There is a loop here in case of 4, then there is this, then there is this, then there is a this, then there is a loop for 5, then there is a 1, 2, 3, 1, 2, 3. There is a and 3 also like this. Okay, so sort of this edge will originate here, and it's what it says here that 5 I have edges from 4, 3, 2, 1. All the edges I'm having for 5. For 4 I'm having edge from 3 and then 2 and then 1. For 3, 2 and 1, and for 2 only one edges here in this case is present. Now let's see the smaller instance here, that if I say that I have to find out all the spanning tree originating from 2. In this case, you will say that only 2 spanning trees are possible, only 1 spanning trees are possible that originate from 2 and goes to, in this case, is 1. Okay, 2 to 1, only 2 to 1, only single spanning tree is possible in this case. Now, if I just say that, okay, what about the 3, how many spanning trees are possible? Now, here I can say that 3, I can say spanning tree, 3 to 1, 3 to 2, like here in this case. If I say that 3 to 1, this is one spanning tree, 3 to 2, there is a one spanning tree, and then there is a 3, and then there is a 2, and then there is a 1. This is also a spanning tree possible, directed one. Okay, so 3 to 2, 2 to 1 is possible, 3 to 1 is possible, and that's all 2 spanning trees are possible in this case. So the from vertex 2 to 1 only single spanning tree possible, from 3 to 2 and 1, from 3 as a original vertex, origin vertex, 3 to 2, 2 to 1, one spanning tree, 3 to 1, 3 to 2, another spanning tree. Let's talk about 4 here in this case. Let's talk about 4, and I wish if I could just draw the graph over here one more time here in this cases. Just give me 1 minute so that I can just complete this graph over here, 3, 4 and 5, and I have this, and there is only one edge, there is a 2 edge, there is a 3 edge, there is a 4 edge, and there is a 5 edge. Okay, now I was just saying 4, what about 4? So what can have as 4 as a directed edge, a spanning tree? Now we have 1, 2, 3, all the edges present. This is 1, okay, then we have 2, and then we have 3 in this case. This is one spanning tree in this. Okay, now okay, for 3 we have 2 spanning tree possible. So that possibility I would like to write here, that for 4 I can go for as a spanning tree in this case is goes here in this case is 3, and from 3 I can go to 1, and then I can go to 2. That is possible here in this cases. And for 4 I'll say I can go to 3, and then I can go to 2, and then I can go to 1. That is also possible. Okay, now here I can go to 4, then I can go to 2, then I can go to 1. This is also possible. Then 4 I can go to, here in this case is 3, I can go to 2, then I can go to 3, and then I can go to 1 is also possible. Okay, now here so now we have here in this case is 5 different spanning trees are possible in this particular case, and one more spanning tree I can say that here if I change the ordering of visiting here in this is like here I can go 4 to 2 and 1, and then finally 4 to 2, and then finally here in this case is 3, and 4 to 2, then 3 to 1 is possible in this, and one complete visiting in this particular order is possible. 4, 3, 2, 3, 4, 1, 2 is possible in this particular case. 4 to 1, and then 1 to 2, that is possible. And another spanning tree in this particular case is that is possible is I start with 4. So this is definitely possible, and that looks like here that after 4 I am going to visit 2 and 3. Let's say I'm going to visit 3, 2, and then 1. So now here I'll start with 1, and then I'll go for 3. Okay, I'll start with 1, then I'll go for 3, and then I can go for, here in this case is 2. So that is also possible in this case. So 4 to 1, 2, 3 separately, 4 to 1, and then I go to 4 to 3 to 2, 3 to 2 is possible. 4 to directly 3, 3 to 1, and 3 to 2 is possible. And then 4 to 3, 3 to 2, 2 to 1 is possible. 4 to 2 and 3, Okay, 4 to first I go to 2, 4 to 2, 2 to 1, and then coming back and then visiting 3, 4 to 2, okay, and then 4 to I'll go to 3 and 1, that is also possible. And in this is the 6 different spanning trees are possible, no? 1, 2, 3, 4, 5, 6. Okay, so this is the, and here we can say that undirected version. So for vertex 4 I am getting the, here in this case is 4, for vertex I am getting 3 into 2 into 1, that is total 6 spanning trees are possible in this case. So here that is the idea that we have here in this case is the one spanning tree if it is a single vertex. For 2 1 1 we got 1, and for 3 we got 3 1 2 and 3 2 1, that is something for 2 vertex. And here in this cases for 2 vertex, because I am getting 2, you can see here different ways we can visit 4 1 and 3, 3 and 2, and here in this case is 4 single time, and then 4 2 and 1 and 3 and 4 2 3 and 1 in this case. So that is also possible, 2 2 1 and 3 2 1, total 6. The general case here in this case is I'll start with 4, but I can't draw all the 24. In this case for 5 the number of spanning tree in this case is 4 into 3 into 2 into 1, that is equal to total 24 spanning trees are possible. That is it for the discussion here in this cases, and this is all question asked from this algorithm part. I would say that not a very easy or questions from this particular topic, and while sitting in the examination interpreting a language like this and getting right answer is something really demanding from this part of this paper, that is algorithm. Okay, that's all for this discussion. I hope you enjoyed the session. Thank you very much.